All right, today we are diving deep into an algorithm that pretty much every developer thinks they know, binary search. But we're going way beyond the basics. We're going to master three critical patterns that will seriously set you apart. I mean, what if I told you that you could find one specific item in a list of a billion elements in just about 30 steps? That is the insane power of binary search. But what happens when you don't need just any match? What if you need the absolute first one, or the very last one? Or what if the thing you're looking for doesn't even exist and you need the closest value? That's exactly what we're going to break down. At its core, binary search is really just a simple divide and conquer game. There's only one rule you absolutely cannot break. Your data has to be sorted. Once you have that, it's all about just cutting the problem in half, over and over again. Okay, so picture this. You've got two bookends, we'll call them low and high, at the very start and very end of your sorted list. You jump right to the middle and take a look. Is your target bigger than what you found? Well, then you know it can't be in the entire left half, so you just slide that low bookend up, and poof, half the problem is gone. Is your target smaller? You do the opposite. Slide the high bookend down and discard the entire right half. You just keep doing that, chopping your search area in half every single time until you either hit your target or those bookends finally cross paths. Now, your standard binary search is great, but it's got one big weakness: duplicates. It'll find you an instance of your target for sure, but it gives you zero guarantees about which one it is. And this is exactly where interviewers love to trip people up, by asking you to find the very first or the very last occurrence in a sea of identical numbers. So that brings us to the big question here. You found a match. Do you stop? For these patterns, the answer is a big fat no. Finding a match isn't the end of the story. It's just a potential answer, a candidate. Now the real work begins. And believe it or not, the difference between finding the first match and the last match all comes down to a single, tiny tweak in the code. To find the first one, when you find a match, you save that index, but then you keep searching to the left. You're basically saying, okay, cool, I found one, but is there another one even earlier? And to find the last one, you do the exact opposite. You find a match, you save it, and then you keep searching to the right. That's it. That simple change is all it takes to completely bias the search. But what if the element you're looking for just isn't in the array at all? Does the search just fail and give up? Well, the next logical question is, okay, if it's not here, what's the closest thing to it? And this is another super common, super practical problem you'll run into. So for this one, and this is the cool part, you actually let a standard binary search run its course and fail. You let it go until the low and high pointers finally cross over each other. And here's the magic. When that loop stops, the true closest value is guaranteed to be one of the two elements right next to where your pointers landed, the elements at index high and low. All you have to do is check those two neighbors and see which one is closer. It's that simple. And that's the absolute key insight right there. Once that search space collapses down to nothing, your answer is trapped between those two pointers. Now, of course, you have to think about edge cases, right? Like, what if the search goes off one end of the array? And you should always have a clear tie-breaking rule. So if two numbers are equally close, you just say, I'll always pick the one with the smaller index. Done. Okay, so we've seen how powerful these patterns are, but let's dig into why binary search is just so ridiculously fast, and talk about some of the classic bugs that can sneak in and trip up even the pros. You're going to see this term everywhere, O log n, or logarithmic time. So what the heck does that actually mean? Well, in simple terms, it means the search time grows incredibly slowly, even when the amount of data gets huge. You could double the number of items in your array, and it only adds like one extra step to the search. It scales like a dream. I mean, just look at this comparison. It's not even a fair fight. A linear scan, that's O of n, has to check every single element in the worst case. Its workload just goes up in a straight line. But binary search, O of log n, its workload barely even moves. The difference isn't just big, it's exponential. Let's make this totally real. To find one number among a billion sorted items, a linear scan might take a billion operations. Binary search, it takes about 30. 30! That's the difference between waiting for minutes and getting an answer instantly. It's a whole different reality. But, of course, with this kind of power comes a few hidden traps. And there's one bug in particular, a famous one, that was hiding in plain sight for years in a ton of official code libraries. It's called integer overflow. So here's the deal. The way everyone thinks to find the middle is just low plus high over 2. Makes sense, right? But what happens when low and high are huge numbers, pointing to indices deep inside a massive array? There's some can actually get so big it breaks the integer. It overflows and wraps around to some crazy negative number. Your mid is now garbage. The safe way, low plus high minus low divided by 2, does the exact same math, but it voids that massive intermediate sum. It keeps you safe.
Okay, so we've got the theory down. Now, how do we package all this knowledge up to absolutely crush a technical interview? Let's talk strategy.
All right, listen up, because this is your interview playbook. The second they give you a search problem, here's what you do. First thing you say is, okay, assuming the array is sorted, we can use binary search. Boom. Then you confidently state the complexity. O of log n time, O of 1 space. Mention you'd handle edge cases like an empty array. If it's the closest problem, clearly state your tie-breaking rule. And then, for the bonus points that show you really know your stuff, you mention the integer overflow bug and use the safe formula. Ticking these boxes shows you don't just know the algorithm, you know how to use it in the real world. All right, let's wrap this all up with a quick summary. This table right here is basically your cheat sheet. For finding the first or last element, finding a match means you log it as a candidate, and then you keep searching left or right. For finding the closest element, if you get a direct hit, you're done, return immediately. But if the loop finishes without a match, all the important logic happens after the loop when you compare those final 2 neighbors. So I'm going to leave you with this one last thought to really lock in that final pattern. Your binary search for something that doesn't exist is over. Your low and high pointers have crossed. Where is the answer hiding? It's always in those 2 neighbors, high and low. Master that concept, and you've truly mastered one of the most fundamental patterns in all of programming.